Welcome to the second threshold of big history, the story of stars. At one point in our universe's history, stars didn't exist, and then the first one was born, and at that point, everything was new under the sun. This new structure was a large gas ball that was maintained in size and appearance for millions of years due to nuclear fusion occurring in its core. For later stars, this amount of time could go on for trillions of years. This first star sent streams of energy into the surrounding space, which provided a new constant supply of energy that would become very important later on for things like us and other complex chemistry on our and perhaps other planets. Because of this feature of sending streams of energy into the surrounding space, stars add something new and complicated and necessary in the buildup of complexity towards us coming to be, and that's why it gets included in this story of big history. Stars are also the story of making heavier and heavier elements, but that's the third threshold, so we're going to take a look at that in another video. This second threshold of the first stars first occurred 200 million years after the Big Bang, and it's been happening ever since. And it will be happening for much longer into the future than there has been a past. It's going to be happening until the universe freezes out as entropy becomes more and more noticeable across time. So, let's now tell the basic story of the first stars and all the stars afterward. Stars are the building blocks of galaxies, so soon enough, galaxies are going to enter the picture as well. The first differences in density in our universe, without which no stars could have ever formed, because if we had a perfectly homogeneous universe, gravity would tug perfectly in all directions and nothing would ever move. Those first differences in density came from quantum fluctuations that occurred during the inflationary period, very early into the first second of history. The quantum fluctuations occurred, as they regularly do in nature, but while normally quantum fluctuations continually go up and down about an average energy level, these quantum fluctuations continually shifted that average energy level up and down as those quantum fluctuations shifted and they moved beyond the Hubble sphere. Normally, quantum fluctuations maintain their quote-unquote knowledge of the average around which they're supposed to hover in energy by virtue of the surrounding space region. They know the energy of the field within which they are, and they maintain that average energy. But because during inflation, space was increasing so much that different areas were moving away from each other faster than the speed of light, as each region moved, it continually found itself in a region with an average energy different from the one that it was in prior, because of the random fluctuations that were occurring therein. So this effectively gave these new quantum fluctuations a new mean around which to hover, either slightly lower or slightly higher than the mean with which the inflaton field started, and that created slight differentials in density from place to place. And finally, when the inflaton field decayed, this density differential was passed from the vacuum energy that was bringing about inflation to the dark matter and ordinary matter and radiation, all the fields of matter that we're more familiar with. And those density differentials were then printed in the world of ordinary matter. And they only continue to grow from there on. Here's how they did that. Once the inflaton field releases its energy, the expansion of the universe continued, but far more slowly, because without the vacuum energy to drive it, it's just living off of the momentum of inflation. And once that happens, the differences in density from place to place begin to matter a whole lot more. Because as the universe expands, matter pulls back on expansion. So regions that are denser experience slower expansions because they pull back on the expansion more than regions with less matter. So from right after inflation up to 57,000 years in, while the universe was dominated by radiation and thereby prevented from collapsing gravitationally, the differences in relative density grew and grew as thinner regions expanded more rapidly, thus thinning out ever more, and denser regions expanded slower, thus thinning out at a lesser rate. But what this means is that despite the fact that differentials in density are becoming more pronounced, are becoming more drastic, one region relative to another, still the average density of every region is getting lower because expansion is taking place in every region. But this would change, at least for dark matter, 57,000 years in when matter became dominant over radiation. So in the year 57,000, the universe transitioned from being dominated in mass total by radiation to being dominated in mass total by matter. And that includes both dark and regular matter. That's important because in matter-dominated spheres, or universes in this case, gravitational collapses could occur, while gravitational collapse can't occur in a radiation-dominated universe. I should mention it's not really a radiation-dominated universe that makes gravitational collapse not occur. It's really when the universe is dominated by a mass form that's moving at relativistic speeds, that's moving at the speed of light. And radiation does that normally, but even the other particles that were around in the early universe that were ordinary matter particles, in the early universe, they were moving around at relativistic speeds as well. So they would have also prevented any gravitational collapse from occurring. At this 57,000 year threshold, when matter becomes more dominant, suddenly the dark matter, which doesn't interact with electromagnetic radiation, promptly began to collapse gravitationally. But the matter, despite the fact that we're not in a radiation-dominated universe, and the matter is being pulled to collapse towards these denser regions that are becoming denser and denser as the dark matter falls, still, the matter, because it interacts with electromagnetic radiation, and there was still so much of it, it still felt intense pressure due to the mass amount of radiation that was pressing on it, and this prevented any sustained collapse. So the dark matter is falling into these huge dark matter halos, and the matter, for the next 323,000 years, just bounces toward and back as it feels the pull towards the dark matter, but then bounces back due to the radiation over and over until 380,000 years. But at 380,000 years in, the universe reaches 3,000 Kelvin, at which point electrons can no longer be knocked off protons and other nuclei, so the electrons attach themselves to the nuclei and the charged particles of the universe. These nuclei and these electrons are all made neutral as they come together and cancel each other's charge out, and the radiation is released to fly freely because it no longer is running into charged particles as it travels through space. Once the radiation is traveling freely, that releases the pressure that the radiation is imposing on the matter, and at 380,000 years, the ordinary matter of the universe begins to fall gravitationally in a sustained collapse towards the dark matter halos. Even though gravitational collapse is actually happening, despite this gravitational collapse, the universe still had a force that was thinning it out. So while gravitational collapse could happen now that the universe is dominated by matter, and for ordinary matter because the radiation pressure had let up, still no regions of the universe were dense enough to halt expansion. So while they continue to get more dense from collapsing, they also continue to thin out some through expansion. This goes on until 100 million years in, and in 100 million years, the densest regions in the universe halt their expansion, and they begin to collapse in a far more significant way. This time, the region is actually growing much more dense as the local expansion is halted by the mass that the given space region has, and now a wholesale collapse goes down, and the second threshold is knocking. For the next 100 million years, the densest regions continue to grow denser as the ordinary matter fell towards the center of these dark matter halos, and as gas built up in the center, radiation was released by the interacting particles, and the gas cooled, and it settled some more, and that allowed the mass to build up and the gravitational pressure to grow, which in turn heated up the center of the gas cloud, and that brought about nuclear fusion of hydrogen into helium, and thus the first star was born. And you'll notice that it took about 100 million years for that to happen, from the collapse 100 million years in to 100 million years later. And those numbers are symmetrical, 100 to 100, and that's roughly true with all of the collapses. These are the densest regions that are collapsing right now. These are the regions that started collapsing first, before any other regions, at 100 million years in. But regions that weren't so dense at this point, but became dense enough such that at 200 million years in, they started collapsing, they would take 200 million years, and so on. The amount of time that the universe was expanding prior to the collapse in whatever region, that's the amount of time that that region will take to collapse. Back to these first stars. These first stars were massive. Likely all of them went supernova before collapsing into black holes, because they were likely all larger than 25 times the size of our sun. Some may not have, though, and they may have gone supernova and just remained as a neutron star. Regardless, these dark matter halos that housed these first lone stars felt the pull of the other dark matter halos in their region, and whether it was groups of stars or groups of black holes or groups of neutron stars that came together, with time, the coming together of these dark matter halos and stars and neutron stars across time brought about larger and larger areas filled with all of these things. And with the second generation of stars, they definitely would have had some survivors and not all died in supernovae and remain as black holes and neutron stars. In fact, after the first massive born alone stars began to be born in groups in similar ways in which they are born now in our galaxy. And these groups clustered with other groups, and more stars were born until you have enough to satisfy whatever it is that your criteria is for a galaxy, presumably anything bigger than a star cluster, I would guess. But either way, the oldest galaxy we see is GNZ11, and it's from about 400 million years into history. That's just 200 million years after the first stars, and this galaxy is already going strong. It has about 1% the mass of the Milky Way, so the universe is clearly off to a very fitful start, and I should mention that there are a lot of other reasons to believe that the universe is off to a fitful start, such as quasars and the general size of early galaxies. We'll return to the development of galaxies soon, but first let's consider the broader story of star birth. These first stars were massive, and they were massive because of their composition. They were made almost solely of hydrogen and helium, which were the only elements coming from the Big Bang. A little heavier matter, though, goes a long way when it comes to forming a star. So the second generation stars, which were seeded with some heavier elements from the prior generation of exploding stars, they cooled faster because heavier elements have more electron orbitals and therefore more ways of releasing radiation, so they were able to collapse more fully without as much total mass. They didn't need as much mass to bring about as much pressure because they were able to get more and more dense internally from releasing more and more radiation much more quickly. This made for, on average, smaller stars from then on. These supernovae and the colliding galaxies send shockwaves through the gaseous atmospheres of these infant galaxies, and those shockwaves sent off mass amounts of starbirth. If you look at GNZ11, for example, it's experiencing starbirth at 20 times the rate of the Milky Way. In the early universe, galaxy collision was the norm, as small galaxies grow through colliding and merging with each other. And the reason why this is happening all the time is because there are tons of them in comparison to now, because so many of them have collided to grow bigger, and also the universe was smaller, so it was much denser then. So it's much more galaxies in a much smaller space, which is why you have much more collisions then than you do now. Although you have, I think, about 2% of galaxies are colliding right now. And at least in part because of this story of galaxy collision and the shockwaves that sends and all of that, starbirth is going crazy as well. And if you look at the history of starbirth, you'll see that somewhere between 2 and 3 billion years, between 10.7 and 9.7 billion years ago, the galaxy collisions in the universe peak, and so does the amount of starbirth. And ever since then, the amount of collisions and the amount of starbirth has been going down and down and down, up until today. If you look at the first galaxies, they're not shaped like many of the galaxies now. Instead, they're a very irregular bunch. They're erratically shaped, and they look like hodgepodge collections of tons of stars just stuck together gravitationally. But because the early universe is buzzing with many of these fairly small galaxies, and most of them are colliding regularly, that's changing. When they collide, they grow. And across time, they also adopt more and more familiar features and shapes. For example, many galaxies have tidal arms. The reason why you call those arms coming off of the galaxy tidal is because the gravitational effect that's giving rise to them is the same in type to the moon's effect on the tides on Earth. But this feature of tidal waves occurs, for example, when a galaxy flies by a galaxy, and it distorts the outer layers of the galaxy and tugs them outward in a complicated manner, and you begin to see these tidal arms in an S shape about the galactic center, one towards the passing galaxy and one away from the passing galaxy. If when a galaxy experiences a significant enough collision rather than a flyby, the centers will collapse fairly fast, during which, if they're gaseous galaxies, some of the gas is going to be heated and flung out beyond the galaxy, and some of the cooler gas will settle towards the center of the galaxy and get compressed, and it will heat, and it will birth tons of stars. And in the case of big spiral galaxies that collide, these so-called starburst galaxies that are created in the aftermath as all these stars are being birthed in the center, they send tons of the gas that's there out of the galaxy and any remnant gas in the galaxy out, and the entire galaxy gets cleared of gas aside from that center. After this around 100 million year period of starbirth in the center of these galaxies from the fallen in gas, the galaxy is out of gas, having consumed it in making stars and expelled much of it beyond its limits, but the galaxy retains some faint tidal features for some time, and eventually those are wiped out, and the remaining galaxy is a birthless elliptical one. Now, despite it taking numerous collisions to make a spiral galaxy, there are some in the fairly early universe. The most ancient spiral galaxy yet detected comes from the 1.4 billion year old universe. They would have first formed in denser regions where collisions were more common, and they have grown more common across time. Therefore, they were very rare indeed 12.4 billion years ago when we're looking at this most ancient spiral galaxy. With time, more and more spirals grow, and by 8 billion years in, they're commonplace. A spiral galaxy's three main structural features are the halo of dark matter, which you normally can't see, but here's what it looks like. It's the blue thing around the entire galaxy in this image, and the bulge of stars in the center, and the fairly flat disk of gas and stars revolving around that center. Now, this halo and bulge come about during the merger. Like I said, when two galaxies will collide, immediately their centers will come together and very soon start birthing tons of stars. So the merger that made the galaxy makes the halo and bulge. But the disk happens across time, as across time, more and more gas from outside the newly merged composite galaxy gets pulled in and gets spun around with the angular momentum of this galaxy, and it builds these rings and bar shapes and other complicated features of spiral galaxies. As we run out of having a lot of gas to fly into the galaxy, the disk just settles into a steady rotation, and it spins around the center of the galaxy. The spinning itself brings about perturbations in the gaseous clouds, and future supernova will do that as well. And in that gas is born a new population of stars swimming in the spin of the gas from which they emerged. But spirals aren't the most common. Elliptical galaxies are. That's in part because, as mentioned, when spirals collide, the beautiful shapes are broken up, and what's left is an elliptical galaxy. What happens is two spiral galaxies could collide, and their dense centers are tugged into each other quickly, creating a much larger new center of mass. We've met that. While the disks are destroyed, the faint tidal features are slowly washed out until we find an elliptical galaxy. And there's a dead galaxy without any gas left, and all the stars are just going to age and age and age, which is why nowadays we never find young stars in elliptical galaxies unless that star just recently stole gas from a nearby star, so it looks young even though it's not. It's tricking us. Because collisions kill spiral galaxies, they make them into ellipticals. In order to be a spiral, you have to maintain a certain degree of solitude, or else you're going to get smushed away. So spirals are most often found away from other galaxies, in the so-called field of galaxies, where lone galaxies are just independently floating around. Now, it's not like you can't find them in groups and in clusters, but the fact is that they're rarer the more dense the region. When you're in a cluster, the center of the cluster, Milky Way-like galaxies, these beautiful spiral galaxies, are most rare, and as you get farther and farther away towards the edge and then eventually to the field, that's where you find the most spiral galaxies. So across time, galaxies are colliding, and they're maturing, and they're just going through their natural aging processes, and they're maturing and maturing. Until today, most of them are elliptical. There are other ways in which galaxies mature than the ways that I've mentioned. For example, large galaxies can eat smaller galaxies, just gradually incorporate them into their shape, like our Milky Way is currently doing to the Large Magellanic Cloud, which is itself accused of having consumed smaller galaxies prior. And there are other ways that galaxies grow and mature than that as well that won't be covered in this video. But the basic story is one of galaxies colliding and making bigger and often more interestingly shaped galaxies with time. Collisions also bring on fits of star birth, which brings increased chemical complexity and provides countless local sustained streams of energy. As the star undergoes fusion and spreads a flow of energy to its surrounding region for millions to trillions of years. With time, more and more galaxies grouped and clustered together and went from small and irregular to large spirals and ellipticals, which we see around us. The gravitational collapse only collapsed relatively local regions, however, and beyond the level of galaxy clusters, mostly everything is moving away from each other. No collapse has ever occurred there, nor will ever occur there. On that scale, the universe has been and will be forever expanding. That's our tale of the second threshold of big history, stars.